9L, limits and continuity. The definition of a limit is that a limit of a function is the value of y that the function approaches as x gets closer to a particular value. We can use an example to demonstrate this idea. So say I have a quadratic and its turning point is at 1 and 2. So what if I say, what is the value of the function or the graph as x approaches 1? So that means as the graph is getting closer and closer to the value of 1, what is the corresponding y value that it is approaching? And it is clear that that corresponding y value is 2. The way that we write the limit of f of x as x approaches a is in this particular form here. So it's the limit as x approaches for a of the rule. The main condition of the limit existence is that the function has to be continuous at x equals a. We will discuss discontinuity in a little bit. A limit will simply not exist at x equals a if there is a discontinuity across an interval and x equals a lies within this interval. There are several types of discontinuities that we can recognize just by looking at them. One of them, for example, is a jump. So if we have a hollow value, we could have a particular graph and then another graph where it doesn't join. We could have a graph that approaches an asymptote. And there you can see that there is a clear discontinuity at this point. So there are several different types and it's quite easy to recognize them visually. We will work out how to recognize them algebraically in a little bit. In order to be able to evaluate the limit, there's pretty much one simple rule, and that's to substitute a number into the function to be able to see what the limit will be as it approaches that value. However, there are times that you can't just substitute it in. So there are times, for example, where if I have a graph of 2x on x, I can't just substitute in the limit as x approaches 0 because then that will make the denominator equal to 0. So what we will have to do in this case is first simplify. Often that will be through factorizing, so I may need to simplify, and then I can substitute in my value. In your final answer, always state whether x is unable to be equal to a certain number. So that will often be when the denominator will make it equal to 0. There are some limit theorems that will also help you to evaluate limits. So just quickly running over all of them, the limit of a constant is equal to the value of the constant. So if I'm taking the limit of just a value, no matter what it is, that is just going to equal that same value because essentially I can't sub x into it. I can't substitute a value for x, it's just always that value. If I have more than one term, what you can do is separate the two terms and substitute them in separately. The same goes if you are multiplying two terms. You can separate those and multiply the limits separately. And of course, the same goes if you are dividing two terms. So you can separate those and then substitute in separately. Let's use all of those rules and ideas to be able to evaluate some of the limits. So for example, 18, it says find the limit as x approaches 1 of this particular function. If I were to substitute 1, I won't have any issues with the denominator equaling to 0. So I can just straight away substitute 1. That will be 1 minus 2 plus 3. That will be negative 1 plus 3, which is 2. Therefore, the limit as x approaches 1 of this function is equal to 2. Example 19. Find the value of the limit as x approaches negative 3 of this function. In order to make this function demonstrate the idea of needing to factorize before we can substitute in, I'd like you to just change this to a plus 3 in your student notes. So we will work with a positive 3. So now when I'm trying to find the value of the limit of as x approaches positive 3 of this function, what I'll notice is if I do substitute in 3, 3 minus 3 is equal to 0, which gives me a denominator of 0. So that actually won't work. So before I do that, I will need to factorize and simplify. So what I'm going to do at the top, if you can recognize, this is in the form of a squared minus b squared, so this will be x minus 3 and x plus 3. And that will be over x minus 3. Because I haven't taken the limit yet, I must continue that notation. So the limit as x approaches 3. I will first simplify. And now that I don't have any more issues in terms of substituting to give me a 0 denominator, I will substitute that in. So this will just simply equal 3 plus 3, which is 6. For example 21, we're going to evaluate a few more limits. For part A, you can see that if I were to substitute in x as 2, I would end up with a denominator of 0, so once again that won't work. What I'll have to do is to factorise. Now I can take the 2 out at the top. If I take 2 out, that will leave me with x squared minus 4, and then what you may recognise is that x squared minus 4 is in the form of a squared minus b squared, so this is in fact x minus 2 and x plus 2. That's all on x minus 2. X minus 2. Because I have not yet taken the limit, I must continue this notation downwards. This is great because now I can simplify these 2 out, so that will be the limit as x approaches 2 of 2. And now all we have to do is substitute in this value of 2 to be able to evaluate what the limit will be. So that will be 2, substitute 2 in, plus 2. That's 2 times 4, which is going to be 8. For part C, it looks a little bit more complicated. If I were to sub in 1, I would get 1 minus 6 plus 5. 1 minus 6 is negative 5, and negative 5 plus 5 will be equal to 0. So that doesn't work. X cannot equal to 0 here. So what we must do is to factorise again in the hope that we can simplify. So that will be the limit as x approaches 1. Factorise the top, so two numbers that multiply to give me 2 and add to give me negative 3 is negative 2 and negative 1. And at the bottom, two numbers that multiply to give me 5 and add to give me negative 6 is negative 5 and negative 1. So this is really nice because x minus 1 will cancel out. So that will simply be the limit as x approaches 1 of x minus 2 on x minus 5. And now I can substitute 1 into x. So that will be 1 minus 2 and 1 minus 5. 1 minus 2 is negative 1, 1 minus 5 is negative 4, and negative and a negative cancel out to give me 1/4. And finally, for part B, I do recognise now that I worked backwards, but it doesn't really matter which order we do it in. Same idea here, if I were to sub in negative 3 plus 3 is going to give me 0. So what I will need to do is factorise again. Two numbers that multiply to give me negative 6 and add to give me positive 1 will be 3 and negative 2. These will cancel out, so that will leave behind the limit as x approaches negative 3 of x minus 2. And now all I have to do is substitute in negative 3. So that's negative 3 minus 2 will be equal to negative 5. In order to determine continuity at a point, we've already discussed how we can visually recognise this, but how do we prove it algebraically? A function f is continuous at a point x equals 8 if the following 3 conditions are met. So the first thing that has to be met is that the function has to actually be defined. It means you can't have a function that has an open circle. You can't have a function that has an asymptote, because at both of these points here, the function is undefined. So that is for part A. The second one is that the limit has to exist. Now, what does that mean? You may remember this from year 11. For a limit to exist, the limit as x approaches a from the negative side must equal to the limit as x approaches a from the positive side. What that means is if I have a function, say we use a quadratic and we use a turning point of 1 and 2, if I approach the x value of 1 from the negative side, I can see that my y value approaches 2. If x approaches 1 but from the positive side, so we'll go this way, I can see that once again my y value is approaching 2. Therefore this is continuous, as opposed to if I have a function that looks like this. Other than the fact that we can visually see that there is clearly a jump, how do we prove this? Well, if we say that this point here is 1 and 2, and this point here is 1 and 3, if I approach 1 but from the negative side, I can see that y is approaching the value of 2. However, if I have x approach 1 but from the positive side, so this time I'm coming this way, I can see that y is approaching to 3. Therefore, since the limit as x approaches 1 from the negative side does not equal to the limit as x approaches 1 from the positive side, so that's limit does not exist. Therefore, it's discontinuous. For part C, the limit as x approaches a of the function must equal to the value of the function as x approaches a. What we mean by this one, if I just clear the page, if I have a graph, say I have this situation again here, before what we recognised with part A is that it was not continuous. So say this is again when x is equal to 1, and then this is when x is 3. This graph is actually defined at every point, which means that f of 1 actually does have an answer, it is 3. However, what we can recognise is that as x approaches 1, whether it's from the negative or the positive side, it's actually approaching a y value of 2. So here what I can recognise is that the limit as x approaches 1 is not equal to the value of the function at 1, and we can clearly see that as 2 does not equal to 3. So in this specific case, the graph is discontinuous because the limit of the function as it approaches 1 does not equal the value of the actual function itself.